And we are back, and today we're going to do an actual research problem. So let me tell you about an apparatus or a technique that I developed in my research, which is called the mechanically transduced immunosorbent assay, METRIS for short. So what we do in our system is we have a surface, and on that surface there's basically ligands, things that bind. It could be proteins, it can be antibodies, it could be antigens, it could be lipid functionalized lipid bilayers, et cetera, et cetera, et cetera. And I have a magnetic particle, a ferromagnetic particle with a magnetic moment M, a permanent magnetic moment M, and it is functionalized with basically a corresponding binder B here. So I apply a rotating magnetic field, we'll call that B. And this particle will proceed to roll and translate. There'll be some translational displacement depending on the friction between the bead and the substrate. And the friction is determined microscopically by the density and strength of these interactions. Now, this is a technique that's used, and it is a mechanical signal. So lots of times in other assays, like ELISA, it's an optical signal. So especially like in a lot of these rapid tests, you see if you're positive, if you see that line. So this is a technique where we actually see the particle translate and move. If there's not a lot of binding sites, if those interactions are relatively weak, the particle will just proceed to kind of rotate and slip. So again, a nice analogy with our dry friction discussion, because the coefficient of friction will be lower depending on the strength if those interactions are relatively weak or if there's relatively few interactions. Conversely, it will be quite significant if the coefficient of friction is large. So kind of like a tire rolling on a substrate. So we see this mechanical signal. Now, this system presents some problems, right? Because I'm applying basically a magnetic torque. So my magnetic torque is going to be this M cross B. So it's hard to measure what's the force, because really eventually I want to get to how much force is required to break that interaction. If I could calculate that, I could explicitly calculate strengths of interactions or energies of interaction. So I want to move away from this system. I don't want to design something like this. So I need your help. So how can we design a new experiment and basically do a relatively straightforward statics experiment to investigate the system? How can we do that? What can we idealize? Well, we said I don't want to apply a rotating magnetic torque, so how about instead I have my same system here, my bead, but instead of a rotating magnetic field, how about we apply just a permanent magnetic field? So a permanent magnet, this will be attracted. There'll be essentially some force that drives the system to prefer or potential motion in that direction. So now we're starting to cook with gasoline. So let's idealize our system. So, and instead of looking, I can kind of simplify this just like we said with a coefficient of friction. So let's go ahead and say, I want to figure out, I have a magnetic bead, and these beads are relatively small. So the bead has a radius of around, let's say 5 times 10 to the minus 6 meters, or 5 micrometers. My mass of my bead is shown here. I can apply a magnetic force of only a piconewton, relatively small, required for this. And again, my permanent magnet is essentially over here, and I'm applying it at an angle of 28 degrees. So I've got my real system, and I've idealized it, and you see there's going to be at the centroid, there's going to be some weight of the particle, and this. That's it. So what I need to figure out is when I apply this piconewton of force, what is the largest coefficient of friction that will keep us in static equilibrium? So what's the largest amount of friction required to keep that particle from moving? So we've got our system. Free the body. Coordinate system right here. So let's free our body. So I've got my weight, my free body here. I'm going to have a normal force as such. I'm going to have my F sub 2. Remember, it must be tangent to this contacting force. So friction must be tangent here. And it's going to go opposite in the impending direction of motion here. F sub 2 is just going to be mu times F1, and we've got it. So let's go ahead and start, and actually I'm going to, let's go ahead and pull up Mathematica, and let's go ahead and start to play around, or not play around, but let's start to, and I'm going to actually quit my system here. Quit the kernel, and I'm going to do, let's do, excuse me, I need to do Alt-4. Let's roll. Not really. Again, puns, I apologize, but again, I need to entertain myself. I'm going to quit the kernel one more time just to make sure we're good. All right, so let's go ahead and let's start to define what we know in our system. So to do that, I'm going to just kind of scroll. If I could click over here. Come on. My touch screen isn't. Oh, I went too far. I've gone too far. So let's zoom out a little bit. Let's put our Mathematica over here. So I'm going to say that my mass is equal to 3 times 10 to the minus 12 kilonewtons. My g equals 9.8. Therefore, my weight is going to be equal to m times g. My theta equals 28 degrees. My f sub b is equal to 1 times pico, 10 to the minus 9. Very, very small. Femto is minus 15. And I think that's pretty much all that we're, and actually let's go ahead and define our radius is equal to 5 times 10 to the minus 6. Excellent. So let's go down to our free body diagram, and let's go ahead and what's some of the forces. Let's just make sure that, let Mathematica run for a little bit. Some of the forces in the x direction set equal to 0. What are we going to have? We have minus F2 plus FB times cosine of theta times degree. Excellent. F sub y equals 0 is what? Minus weight plus F1 plus FB times sine of theta. Right here. Oops, degree. There we go. So how many unknowns do we have? Oops, little g. Apologies for that. Good to check our unknowns. F1, F2, but I forgot to define here. We said here F2 is equal to mu times F1. So let's go ahead and define that here. So now we have how many equations? How many unknowns? Let's go ahead and solve. Fx, Fy, and we got it. Not too much is required. So fantastic. Nice, easy solution. Thank you all for your help. So this tells us, and we can actually see, okay, if I need to, if the particle doesn't move, I can essentially look at or measure that particular amount of friction doesn't require to move. Now we'd have to essentially tune it where it's just on the verge of to ensure that this is obviously that your the force that you apply it will scale. And actually, let's go ahead and just see how that may change, just to give us some. It's always fun to kind of look at some of the tunable parameters in a system. So let's say I increase it by 8. So we could rerun this solution, solve, and hopefully the coefficient of friction should increase. And we got it. Yeah, nice, fun, really, really cool. Thank you for your help. I'm going to go now take this and do some research with it. So before we leave, let's go ahead. There's a couple of other ways that we can model that system too. So we can actually even think about it a little bit later with springs and actually calculate those as well. So let's go ahead and actually we'll move on to one more fun system, and that is going to be looking at don't jump the gun. So some nice sprinting expressions, and so we'll see you all next time for the next video. Thanks. Bye.